definitely. No. Yes. So the little first homework thing, I'm gonna put that after we get done with this. And it's not good for a while. But what I would like you to do is hand do it, like do it by hand, and then you're just gonna pass it in here. Like, you're not gonna upload anything. But I wanna see where you're at, doing mechanisms, and what your drawing skills were, and stuff like that. So, we can log you back what it all looks like. We got that, and then the other thing I'm gonna do today is put up an announcement about the cannabis conference. So that's in April, and it is in Pueblo. So, Governor Hickenlooper gave money to CSU to start a cannabis research institute, which they did at Pueblo campus. And the chemistry department there is not involved in the research institute, or was not last year when I was down there. But the biology department is, and they're mostly looking at outdoor propagation issues with that. The conference, however, is pretty cool. So it's a international conference. There's a few people there from foreign countries, mostly it's people from all over the United States. There's multiple sessions going on simultaneously, and the topics range from the technical production type of stuff to medical applications. Last year, there was a lot going on about medical applications and stuff that's going on in the pharmaceutical industry. And last year I gave a talk about this class. This is the first technical university level class that was upper division in the country. So I talked about that, and this coming year I'm going to be on panel. We're going to have a panel discussion about teaching in the university, because now there's more people doing it. So that's kind of cool. And the Davis, University of California, Davis, they have a lot of strength in oenology, which is the study of winemaking. They also have a lot going on with fermentation. And so they're like a natural to also have a cannabis class. So they implemented one. I gave up all my materials on my syllabus and everything. they were gonna do that last fall, so I wanna find out how that went with them and all of that kind of stuff. So there's a lot of interesting things at that conference. It's pretty cheap for students, and it's in Pueblo, which is an easy drive. It's typically on the weekend, let's see, I think it's maybe Friday, Saturday. I think I drove home on Sundays. But I'll post y'all the information and you can look at it. The plenary speakers are definitely good, and they are people who have been doing this their whole lives. So it's definitely worthwhile and big networking opportunity if you're looking for a job. All right, so what we're going to talk about today is we're going to talk about how to make isoprene, which is like the first level terpenoid. But in order to make isoprene, we have to make methylonic acid, which is the building block for the MBA pathway. And so that just doesn't come naturally. So we have to make that, and we make that from acetyl-CoA. Now, if you look in the Do-It book, I've got like, I don't know, 16 slides for this, because what this is like typical of either like professional papers or advanced textbooks where they will consolidate all these reaction pathways into like the minimal amount of a scheme. So basically what you have is, this is exactly from the textbook. It is the scheme, and when you look at the schemes, a couple of things you need to know about is like the E's here refer to enzymes that are necessary to function as catalysts in these kinds of biological situations. They will only give you the arrow pushing parts on an incredibly minimalistic level. And the assumption is that you know how to fill in all the gaps that they are not showing you. So what we're going to do is we're going to do all the gaps, because for some of you it's been a while. All right. So first of all, we want to talk just about aldol and Claisen reactions. If you've had O2, you already know this. If you haven't had O2, then this is all new. So, all right. So aldol and Claisen reactions are very similar. The only difference between the two styles has to do when the base either attacks an aldehyde or ketone, or when the base attacks a carboxylic acid derivative. So so aldehydes, those are carbonyls that are bonded to a hydrogen on one side and an alkyl group on the other side. Ketones, carbonyl group bonded to two alkyl groups, one on each side of the carbonyl. Carboxylic acid derivatives, if you forgot what those are carbonyls, and then on one side there's an alkyl group, and on the other side there's like a hydroxyl group, that's carboxylic acid. Or there's an ether linkage, that's an ester. Or there's a amine linkage, that's an amide. Right, so there's all these different kinds of functional groups that are carboxylic acid derivatives. The ones that we are interested in the most are esters or thioesters, which are the sulfur analogs of an oxygen ester. So in terms of, that's like the functional group world we're looking at. And in terms of how the reaction works, first of all, we're going to take advantage of the fact that protons that are in the alpha position to a carbonyl are acidic. So here's my carbonyl, here's my alpha carbon, next door neighbor carbon, and they're acidic because of stability of the conjugate base. Okay? So this is the conjugate base. So those are acidic protons. They can be removed by a base. When you remove them by the base, you can look at either this arrow pushing concept where the pair of electrons in this bond forms a pi bond right here. The pi bond breaks and dumps out a pair of electrons right here. That gives you this resonance state. Or you could just think about it as phase rips off this proton, and the pair of electrons in this carbon-hydrogen bond are left right here on this carbon, which leads you to this resonance state. Okay. So these are two resonance states of what we call an enolate anion. So enol means ene for the double bond right here, and the OL is for like OH. So it's an enolate anion, and because that negative charge can be delocalized over two atoms, a stabilized conjugate base. So stable conjugate bases go with what did it say? Stronger acids. All right, so so the acidic proton gets removed to make the enolate. So that's the formation of our base. In a biological system, the species that acts as a base is typically some kind of enzyme, and it's like pH driven, has to do with what the pKa's of the underlying starting materials are. All right, so once we get the enolate, then the key feature of both aldehydes and plazin is the enolate then attacks another carbonyl containing species. Okay? So the enolate, so that if you think about a carbonyl, there's two ways to think about a carbonyl group. You can either say, oh, well, oxygen is way more electronegative than carbon, so that area between the carbon and the oxygen is going to be polarized. That's going to give me a partial negative charge on the oxygen and a partial positive on the carbon. If I have a partial positive on the carbon, it's going to be electrophilic. It's going to be attacked by nucleophile. You can think of it that way, or you can say, okay, I have a carbonyl group. Carbonyl group is actually a resonance hybrid. I draw it, just C double bond O, that's a Lewis structure. But I could also draw it where I break that pi bond and dump a pair of electrons on the oxygen. So I have a full positive charge on the carbon and a full negative charge on the oxygen. And so I have those two resonance states, and the reality of my molecule is that it's a resonance hybrid, and it actually is, you know, partial positive on the carbon, partial negative on the oxygen. So you get to the answer by two different routes of thinking, right? But carbonyls are nicely electrophilic, so anything that you have nucleophilic handy around is going to be able to attack those guys, right? And nucleophiles, you have like oxygen-containing nucleophiles like water. You have nitrogen-containing nucleophiles like amines, right? And you have carbon-containing nucleophiles like enolates are a classic one for that. Okay. So the carbon nucleophile enolate attacks the carbonyl, breaks up pi bonds outside the pair of electrons, and so now we have what was an sp2 hybridized carbon is now a tetrahedral intermediate. It's sp3 hybridized carbon, and then what if X is a good leaving group, then what I can do is reform that carbonyl and dump X out. Okay. So if I do that, I end up with this kind of product. Right, so this is like a dicarbonyl, type of compound. What if X, especially when X is a poor leaving group, then I just deprotonate that O minus, and I get this aldehyde type product. So if X is an aldehyde, I mean if it's a hydrogen, you have an aldehyde, then H is a poor leaving group. You're not going to leave as H minus, right? H minus, its conjugate acid is H2, and H2 has a pKa of way up in the 40s. So H minus is going to be a super strong base. And so you're not going to dump that out. If you have a ketone here, then X would be an alkyl group. Same thing, you're not going to dump out an alkyl carbanion type group, right? Because its conjugate acid would be a hydrocarbon, and hydrocarbons have pKa's like in the 50s, right? So they're super weak acids, so their conjugate bases would be really strong. So you figure out what's happening based on what the structure of the reagent group is. And so we're going to be going about this. All right. Alright, so you know what an ester is. So an ester is when you have a carbonyl and you have an alkyl group on one side, and then you have like an ether linkage on the other side. So a thioester is just a sulfur analog of that. But it turns out that thioesters are more acidic than a regular ester and have a pKa of about 21. So that difference right there just makes it so much easier to remove the alpha proton with a base. Right? The alpha proton would be on this carbon right here. That's the alpha proton. So let's just look at a couple things. All right. We look at this like in OChem 1. So we know, like, if we have a generic acid, right, we have a generic acid, and we just dissociate it into the conjugate base plus H plus. Right, then if we just look at that as a reaction, then HAs are starting stuff, A minuses are ending stuff, and we can figure out what our equilibrium constant is, and we can also figure out what delta G is between those guys. So we know, and that's the relationship of that, like delta G defines our T log KQ. Alright, so if you think about it, okay, strong acids completely dissociate, right? So then you have 100% A minus and basically 40% of HA. And the equilibrium is all the way to the right in that kind of scenario. In that kind of a scenario, delta G is going to be negative, right? You think about like up there, what log KQ is going to be. All right, if you have and the pKa will be negative. If you have a positive pKa, that's telling you that your HA is not going to be completely dissociated. The higher the pKa, the weaker the acid. The weaker the acid, the less A minus you're going to have when you're just looking at the dissociation. Right? So, if you have a positive pKa, then you're always going to have a positive delta G because you're going to have an endothermic scenario. And you want to also consider that this is a two-variable situation. So the difference between 21 and 24, that's 3 orders of magnitude, right? Because it's the pK, just like pH, it's a logarithmic way of communicating. So the difference between something that has a pKa of -10, which is like super acidic, to something that has a pKa of +50, like a hydrocarbon, which is hardly acidic at all, that is like 60 orders of magnitude or so, which is a huge, huge, huge differential. It's like almost incomprehensible having a 60 order of magnitude difference. So even though it looks like, okay, pKa of 21 to 24 isn't that big a deal, 3 orders of magnitude is significant, especially in biological situations. Okay. So, and these are two variable problems. So if I want to figure out why I have that difference, then either I could, if I stabilize HA, I bring this down. If I leave this about the same, that would give me a higher delta G positive. Or I could stabilize. So if I can move this one up or down and go either higher or lower, or I can move this up or down and go higher and lower, and still stay in the correct domain of delta G. So if I look at both of those scenarios with my thioesters, right, I can either look at them both as acids, or I can look at them both as bases. So let's do the base first. So I look at my base, and essentially I have the same scenario going on that I have with a regular oxygen ester. Right? I can, I got 2 resonance states, and so the main thing that's happening with the stability of A minus has to do with the number of resonance states and the delocalization of the negative charge, and that's basically all the same. So that's not going to help me too much. But now if I look over to what my starting material looks like, right, so here's my oxygen ester. So I can think about my ester from a resonance hybrid point of view, right? So I have a lone pair next to a carbon that's sp2 that's involved in this carbonyl. So I can think about it from a resonance point of view, where I have the charged species over here. So plus charge on oxygen, not that hot, because oxygen's electronegative, and negative charge on oxygen, but everybody's got hot cat, so that's not that bad in general. All right, but now if I look at the thioester scenario for that, then I got a plus charge on sulfur, which is less favorable than if I have it on oxygen. Okay. So my resonance hybrid is going to be higher in energy, right? So my HA is higher in energy, but my A minus is basically about the same energy, right? So that's where I get my difference in the pKa. So small differences in the structure can lead to big differences in how things function in the biological system, which is very sensitive to pKa. All right, so what we do is we have acetyl-CoA, and we have, so on that acetyl-CoA, we have some kind of enzyme that comes along and functions as base and breaks off that alpha proton and gives us our enolate. Then I have this acetyl, so it's like if you have the acetyl SH, which is SH would be the thiol, that can bind with an enzyme, so you have a sulfa enzyme linkage, and this is just essentially a setup for being a thioester. So now my enolate attacks the carbonyl of the thioester, so I put the two together. My carbon hybridizes to sp3, I have a tetrahedral intermediate, and I have a nice little leaving group right here. So I can reform the carbonyl and dump out that leaving group, and so now what I've done is I put like an acyl group on my acetyl-CoA. So I have extended my carbon chain. So in terms of what kind of functional group this is a beta-keto-thioester. So here's the thioester part. Here's my alpha for that. That's the carbon, right? Carbonyl, and then here's my beta. And then I have, I'm sorry. So here's my thioester, here's my alpha carbon right here, and then here's my beta carbonyl. Okay? And alkyl group, so that's ketone. So that's where the beta ketone thioester comes from. So that's just a biological Claisen reaction. Right, we just talked about that. All right. So once I got that going, now I can continue. And so along with the acetyl-CoA, and you have the thiol that reacts with the enzyme. Both of those have the alpha carbons, and both of those are going to have alpha carbons in the same pKa range. So I can also remove the alpha proton from the S enzyme, thioester, and then that can attack the carbonyl. Now, one of the things you got to think about is that enolate, it could attack the one that's shown, or it could attack the other one. So if it attacks the other one, it's probably going to end up going backwards, right? Or you end up either going through a backwards pathway, or you make the same thing that you started with. So those pathways may occur in nature and in a laboratory scenario, but we don't pay attention to them because they don't give us the route that we're looking for. All right, so we have enolated attacks carbonyl, breaks up pi bond, that's like on oxygen, and we get this. Now, what's interesting about this, so this is our other map right here, it's for our enolated attack. So, we're generating a stereocenter here. So because we're bound up with an enzyme, we're actually going to generate a stereo-specific stereocenter because the enzyme itself is chiral. So this is like we're going to do the alcohol scenario because we're attacking a ketone and we don't have to do leaving group. So there's no leaving group to leave. If we reform the carbonyl here, we would break this bond, that's to a carbon, not happening, or we would break this bond to a carbon, also not happening. So all we do is protonate it, and then we end up with a beta hydroxydiester. Ester this side, ester that side, that's the diester part. Here's the alpha carbon, here's beta carbon, and there's the hydroxy group. Right? And you can get to the beta hydroxy whether you start at this end or the other end. It's totally even, yeah.
If you're giving an enzyme, does that stop elimination?
Or elimination,
Condensation part of the alcohol?
yeah. So, okay, this is just detailing out what I just said about the two thioesters and the alpha and beta carbon. So in terms of, okay, dehydrating to a, you want it to dehydrate to an alpha beta unsaturated? Yeah, so it's not going to dehydrate to alpha beta unsaturated. like we do like in O2. So instead, what we're going to do is hydrolyze, we're gonna hydrolyze one side to a carboxylic acid, which is like a competing pathway. So what he's referring to is that you can protonate that OH group, and then you can do like an E1 style type elimination and make a alpha beta unsaturated functional group, which is carbonyl next door to carbon-carbon double bond. All right, so instead, what happens here is we have hydrolysis. All right, so what I did is I took like the thioester, that's the CoA end, and I just abbreviated all that as R, because I'm telling you, it's very repetitive, drawing a bunch of this stuff. And we're focusing just on the S enzyme end, right? So, water functions as a nucleophile. So my guess as to why you don't have that alpha beta happening is that at this point, you don't have enough proton concentration in the immediate vicinity to protonate that OH group. Because you would have to protonate that OH group to make it to a good leaving group.
You went like with a basic environment, that would make it one time to the phase.
You could, yeah. Now, so that's the thing, I don't know how regulated that the proton level is at like where this is happening in biological systems, you really have to look at the immediate environment, and look at your proton gradient. So I'm not sure about that, because like here, you just have water functioning as a nucleophile. So water functions as a nucleophile, and now you have an oxygen nucleophile attacking your OH carbonyl group, and it's typical intermediate, right? And if you look at what we got as potential leaving groups, we could go backwards, we could reform the carbonyl and dump the water out, that would go back to the source material, because we know water is a leaving group. Or we could break this bond and these guys leave and the S enzyme leave, and depending on what the environment is for that, it can be a good leaving group. So that leaves, and we have our protonated carboxylic acid, it's deprotonated, and then we have a carboxylic acid in. So let's look at what that is structurally. Right, so that's going to be our product. So remember we put the stereo center in there before. So now we've got that one stereo center made. We still have our acetyl CoA little end piece there, but now we put on like this other chunk. So we're on our way. All right. Then, interestingly enough, so now what we're going to do is use hydride as a nucleophile. Okay? So, in a lot of scenarios, we always protonate carbonyl, makes it more electrophilic. So, depending on what the proton level is, you don't need to have it protonated like full molarity, like 1 mole gets protonated in 1 mole. It's like all you need is like an equilibrium, and you just need a little bit of protonated carbonyl, then that reacts with the nucleophile, and then that drives your equilibrium to the right. So we get protonated, and hydride is delivered by NADH. So it's like reductions biologically occur by delivery system, and, but it's essentially the same as what you learn in organic chemistry when you do reductions. So you're putting on a hydrogen atom plus a pair of electrons. So H minus goes over the nucleophile, attacks the proteinated carbonyl, and now we have another OH on here. Oh, okay. Okay, so if we have, one of the things that we look at in organic is these species that are called hemiacetals. So a hemiacetal is a carbon that has a hydroxyl group on it, and it also has an ether linkage on it as well. So if we look at what we just made, we have a carbon with a hydroxyl group on it, and then we also have a carbon, we also have an S-CoA bonding to that same carbon. So this is classified as a hemidioacetal. And so we can look at what we're doing here. We reform the carbonyl group, and then we can dump out this S-CoA part. Okay? And that gives us this aldehyde functionality, and then we still have our stereochemistry. Now, once we put that OH on, like in the previous step, like we didn't show that we had any stereochemistry, it doesn't matter because it's going to go away. Okay? But probably based on like whatever enzyme is involved in that, it's going to go on in the stereochemistry. We don't care about that. So now we have our aldehyde. And we're almost at the malonic acid. And so we're going to reduce our aldehyde again. And so we put another H minus on there, reduce that, and now we have our CH2OH. So now we have our malonic acid, our MDA, that we made with our intact stereochemistry. So that's all good. So all of that, remember, was all a part of this, right? So, like, ideally, where you want to be at, especially if you're a graduate student, is you want to be able to look at the scheme like that and be able to parse out what all of those steps are and be able to draw your own mechanism for exactly how you get from the starting step all the way through on each one of these steps. Okay? Because so much has been left out. So doing something like this for a mechanism problem is not going to be sufficient. So if I ask you to do a mechanism problem, you then need to produce an arrow to show like every single like movement of a pair of electrons throughout the whole thing. Pharmacologists they don't want to do it. They just reduce it all down. Alright, so NADPH is the hydride delivery system. So NADPH goes from that being the hydride guy, and then the product is being NADPH. So you don't keep track of that. Alright, then the next part is we are going to do the malonic acid, and we're going to get over into like that basic kind of protein structure. And there's two of these. There's the IPP and there's the DNAP. And so we're going to look at those in detail, how we there, and then how they, isomerize to each other as well, and what happens to them. So let's just look at the beginning of this. All right, we have primary alcohol. So, putting on these phosphate groups, this should look familiar if you had organic lung, because you have a primary alcohol and you want to do something with it, you're going to have to convert that hydroxyl group into a better leaving group. Hydroxyl groups are kind of leaving groups, right? OH minus is the, if you look at OH minus as a base, as a leaving group, its conjugate acid is water. Water has a pKa of like 15, which is, you know, it's not too bad, but at the same time, OH is something with these groups. Alright, however, if we can put these phosphate groups on, it's going to convert that OH into a really slick leaving group. And we can, so we need some ATP for this. So here's our ATP, and it's got these little phosphate groups on here. And so we just have our MPA, and it just does an SN2 reaction on that phosphorus and dumps out the ATP part, and we got the one phosphorus group on there. And then, of course, that puts a plus charge on oxygen, and then I skip that step where we just deprotonate it with whatever's around, typically water, and now we've got our on there. So that's our oxygen that did the SN2 on the phosphorus. And then we can do that again, and we can stuff another one on. So now we have our primary alcohol has this really nice leaving group on it. And so you could say, well, I get that. So how come the secondary alcohol on there doesn't get phosphorylated? Right, what would make that less competitive than the primary? Remember, SN2 is conservative mechanism. So the transition state has the bond that you're trying to form partially made, and the bond that you're breaking partially breaking in the transition state. So the amount of steric hindrance in the transition state altogether is going to dictate what the energy of activation is and what the rate of the reaction is. So the rate of the transition state with the primary carbon, so even though it's the oxygen that's making the bond, the primary carbon is like right there, right next door, right? Versus if it was a secondary carbon that would be right next door to that oxygen. So that little bit of energy difference that comes from that steric hindrance is enough to run the rate difference to where the rate of doing it on the primary is fast enough that is what you get. All right. So instead of doing little SN2s and trying to get it into a better leaving group, it has an intramolecular approach to making itself be a better leaving group. So it can suck off this proton that's on the carboxylic acid end, right? And protonate, and so now we have OH2, which is a good leaving group for that. So we have like a good leaving group here, and now here. So in terms of that little process going on, and having that be competitive with if it did a different, you know, the version. Intramolecular does not require collision, so it doesn't, it could be that, it's held in the pocket to where it's really, the proton being, removed is like really close by the pair of electrons, because you have to have the orbitals overlap to make that go. But if you look at it, that is a, like for the transition state, 1, 2, 3, 4, 5, 6. Out of the transition state there, so that's favorable as well in terms of that. So we get that route going. So problem is, now this is a good leaving group, this is a good leaving group. But once we get the proton removed, this carboxylate group then can decarboxylate and eliminate. So if you look at how this works, so we're forming a pi bond here, so this is our CO2, this bond is going to break, paired electron from this bond forms the E here, and that in turn dumps out the OH2 group. So that's how that decarboxylation and elimination works, and that gives us the IPP. Isopentyl diphosphate guy. So now we have a carbon-carbon double bond as a frictional group, and then in the allylic position, so this is the allylic position, then that proton can be as acidic enough that, so we're trying to do what pKa is. But we can have enzyme that is basic enough that can pull that proton off. In terms of if you have forgotten your position, your vocabulary for positions, the carbons that are involved directly in the pi bond, those are the vinyl carbons. So that would be this one and this one, they're both vinyl. And the next door neighbor carbon to the vinyl carbon is the allylic carbon. Right, so we can talk about it as this proton's in the allylic position, or we say this is an allylic carbon, what have you. All right, so enzyme comes along, sucks off the allylic proton, and we have an allylic carbanion, right? So when you suck up a proton, a pair of electrons are left behind, they go on the carbon, that gives us a carbanion. That negative charge can be delocalized, so it can be delocalized over onto this other carbon. So anytime you can stabilize a conjugate base, then that's going to lead to a more acidic, a stronger acid, so that proton is going to be more acidic. All right. So the carbanion can then just get protonated, and if it gets protonated, then we've got the DMAC and the dimethyl PP. And so that's how those two interconvert with each other, the IPP and the DMAPP. And again, so you want to just think about this. So now our leaving group is in a allylic position. So this is primary allylic, and then we have these two methyl groups on one side of the pi bond. So the L group, so the dimethyl L, when you see that, that's like old school nomenclature. And so the L group, L thing is this carbon, the pi bond carbon, and the allylic carbon. So those three carbons together form what's called the L group. All right, so we got the IgG guy and we got the DMAT guy, and they are structural isomers of each other. So let's look at them in terms of what potentially that they could do, what they got sticking here. So we got a good leaving group. We got a good leaving group here. So this would be good, like we're doing SN2 because it's a primary with a good leaving group. But primary with a good leaving group is really bad if we want to have it leave and form a protocation. Like primary protocations are going to be really high energy. So that's not so good in terms of that. We do have a pi bond over here, and we already know like pi bonds are good, they can function as nucleophile. Those electrons in the actual pi bond, which is where the p orbitals are overlapping each other. When the p orbitals overlap each other, there's electron density above the plane and below the plane of where the sigma bond is. And it's that external electron density that allows for it to function as a nucleophile. So we know that can happen. And then we have our DMAP. And if you look at that, well, so this is like primary, you can see it right here. However, this would be a primary allylic protocation, right? And I could delocalize that plus charge to the cathode. So the primary allylic protocation has about the same stability as a regular old secondary, right? So that's a possibility. That's also an inducement position to do an SN2. So they're both competitive in terms of if there's something around that could do an SN2 on them. Right? But they are this is much better in terms of SN1 and SN1 class. Right, so this right here gives you the resonance state. Primary allylic, I can move the tiny electrons from here, from charge here, that's tertiary allylic. So my resonance hydride looks like this. Partial positive charge over here, partial positive charge over here, and my high character across all three of those atoms, right? Standard kind of stuff. So, kind of move it down a little bit. So what I can do is I'm going to have my leaving group leave, make myself my resonance stabilized allylic protocation. That works out pretty good. And then, as you know, and once you get a protocation, it's going to do anything that it can possibly do to stabilize itself because the protocation doesn't have a high energy species. Right, so essentially, anything that can function as a base and pull off the proton will pull off the proton, form these electrons from a catapult bond that form this pi bond, and now we have a conjugated system. And as you recall, conjugation is good, it leads to a lot of stability. If you haven't had O2 yet, in O2 typically we look at molecular orbitals of conjugated systems. And what you should recognize if you had O2 is that when you have conjugation, there's 4 electrons total in those 2 pi bonds, and there's 2 bonds total that are 2 molecular orbitals that cover 1, 2, 3, 4 atoms. Right? So we draw it like that, which really want to think about it as conjugation involves all of the atoms together in one bond. Right? And that gives you a lower energy than if you just have like isolated bonds between two atoms. So typically when you form a conjugated compound, the reaction is driven by the stability of the product. And that's what happens this way. So that's how we get our isoprene. So our IPP just sits there and does nothing, and our DMAP goes to make the isoprene. So that IPP isn't going to sit there and do nothing forever. Right? It's going to react with the isoprene, but we're going to talk about that next time. So isoprene is very interesting as a compound, right? If you look at it in terms of, we talked about remembering last time. So you want to give the mouth blue the lowest number, so you start at the left-hand side with column 1. Right? There's no system trans involved with either of those pi bonds. Right? The two hydrogens on each terminal and carbon. It is a gas. It's just a substitute butadiene. In fact, you can capture that from biological systems, or you can make it from petroleum byproducts. And it is a precursor to making like rubbers and things like that on an industrial scale. But plants, since it's a gas, they emit it all the time. So this is what's crazy, is it's the predominant biogenic source of hydrocarbon in the atmosphere. Right? And it's primarily coming from plants, trees, and all of that stuff. And the homework that you're going to get has to do with the fact that we breathe it out. So we make some too, but not like plants do. Right? And so you'll get that when you read the little article I have about how you detect isoprene in your breath. Right? And so it's like getting pumped out. So I suppose like one of the arguments, and definitely I have seen this argument put forth by various people, is okay, if all these plant materials are dumping out all this hydrocarbon junk into the atmosphere to the level that it's the same as like the global emission of methane, then one of the things that we could do to solve our global warming problem would be like get rid of the trees. Right? So if we deforest, then they won't be pumping stuff out. Not kidding, it's out there. So, but they don't get like, okay, well, the trees are the ones that suck up all the CO2 because they breathe it in, you know? So you just have to like, you gotta like understand like the bigger picture of a lot of these systems. All right. One of the negative things though is isoprene does react with NOx. So at the lower atmospheric levels, anytime that you have combustion, so like anytime if you have like a gas car, you turn the ignition on, you got combustion, wanting to drive in, right? That combustion, so you react with the oxygen and the nitrogen that's in the air. That's what combustion is. So anytime you do combustion, you're going to generate some NOx. So NOx is either NO, NO2, NO3, that kind of stuff. So low-level NOx then can further react and is part of ground cloud. So especially like in Denver, we get inversions. So you get that ground cloud. That's strictly all NOx in the atmosphere. Right? So ground level ozone, which is O3, um, NOx can react with O2, and that can generate the O3. Ground level ozone is bad. That can, if you're asthmatic, cause a lot of problems. Generally, respiratory issues for ground level ozone. Upper atmosphere, ozone is good, right? Because the ozone traps the UV that's coming from the sun, and so you don't get blasted by the UV. UV breaks bonds homolytically, and homolytically means that one electron in the bond goes with one carbon atom, the other electron goes with the other carbon atom, and we generate free radicals. Free radicals are very reactive intermediates, and they're associated with DNA degradation and aging in general. And so our exposure to UV is regulated by the quality of the ozone in our atmosphere. And the atmospheres don't mix very well. There's like very discrete layers in the atmosphere where certain reactions occur. So if you take environmental chemistry, we spend like all semester talking about that, essentially. All right. So, so isoprene has its own pluses and minuses. And I think that's about, so that's it that I have today. And then what we're going to do is talk about next time how we convert isoprene then into that monochrome. So I don't think, yeah. It's carbocation mechanism. So if you remember from like O1, if you do carbocation and it can rearrange, it will rearrange. So you're going to see every possible type of carbocation. Okay.
She has all the slides and posts them after class. She just posts it Yeah, this is the first homework assignment that she assigned. We do have, I don't have.